Hi there, I'm Jason Knight, co-founder and chief product officer here at OctoML, and I'm here with Andrew Lowe, who's one of our amazing ML systems engineers, and we'd like to share a little bit about our experience with ONNX, building a platform on top of the Apache TVM open source project, and some of our learnings that we'd like to share with the ONNX community, and show some cool things that we're working that might be useful for the ONNX community as we think through future improvements. So without further ado, just who is OctoML? What are we doing? Well, we're building the machine learning deployment platform, which is an automated platform for any ML end user to take their model in ONNX or other formats, put that into our system, optimize, benchmark, and package that on a variety of different platforms, both on the cloud and on the edge for many different devices. And we're using a lot of technologies like ONNX and TVM to enable maximum performance and performance portability while making it a push button experience. But the focus of the talk is on the open source TVM and ONNX side and interaction. So let's focus back on that. If you haven't heard of TVM, what is TVM? TVM is an open source project started about 5 years ago, and it's a toolkit designed to enable anyone to achieve high performance machine learning on any device in the cloud or on the edge, or and also to support future devices as well. And so what is the project composed of? Well, at the top, we've got importers from a variety of formats in the TVM. Notably, ONNX is one of our best supported, and offset 13, and where test coverage is really high up there alongside something like ONNX runtime. So really have a great experience there with both users and the community. Then underneath that, all these importers unify down to a single high-level differentiable intermediate representation called Relay that enables rich type subsystem that supports dynamic shapes and dynamic control flow, etc. TensorIR is then our one level lower that allows us to represent and optimize over mutable loop nests. So we can encode patterns like dense and sparse linear algebra in a variety of complex control flow schemes and regimes for both operators today and into the future. And then one of the most important parts of TVM is the machine learning based set of optimizations that we have that enable a naive lowering approach to instead now lower to very high performance code on a variety of different platforms, from CUDA and OpenCL to WASM and WebGPU, SpearV, DirectC, LLVMIR, etc. And it's auto TVM, auto scheduling, and auto TIR that enable high performance code to be generated without strong manual intervention or human expertise involved. And so with that, I'm going to pass it over to Andrew to talk about some of our experience using ONNX in production and where we're going from here. Andrew, take it away.
Yeah, thanks, Jason. So as Jason said, ONNX remains our preferred way for importing models into TVM. It's probably the most well-developed front end for use in TVM, and has helped OctoML launch our platform quickly while guaranteeing high model coverage and being able to talk with a variety of different customers easily. Furthermore, our roadmaps are actually pretty in lockstep with ONNX. As OctoML and TVM thinks about quantization and training support, ONNX also, as we see, has it in the roadmap too. That's not to say that ONNX hasn't had some lowlights in using it. For example, some frameworks, most normally PyTorch, still have problems exporting into the ONNX format, which prevents us from talking with certain customers easily. Finally, ONNX has a certain level of dynamism, which pressure tests TVM's design as a compiler, which I'll go more in depth in the next slide. So by dynamism, I mean shapes and values in tensors, which can only really be inferred at runtime. So you can't look at them at compile time and generate the code properly ahead of time like that. As the one thing we've noticed is that as ONNX gets older and as offsets gets older, more and more operators are gradually becoming dynamic. For example, reduce sum takes the sum of a tensor across a provided axis. In older offsets, this axis was a parameter which was an integer that you could look at compile time and generate the proper code easily. Now in offset 13, axes is actually an input tensor, which it's a little bit harder to do. And we've also seen that this increasing dynamism in the operator offset is sort of done inconsistently at this point. For example, while reduce sum has axes as an input, in reduce min, which is a very, very similar operator, we see axes is still an attribute. And the reason for this, as we've discovered, is probably because ONNX kind of made the minimum amount of changes in order to support execution of training graphs within the framework, which makes sense. So if we go to the next slide, I'll talk about maybe why this is going to be a problem in the long run. And kind of the main point I want to get across is that ONNX really kind of is fundamentally going to be a dynamic framework, because ONNX runtime, the thing which executes ONNX models, the first class citizen which executes ONNX models at least, has a much more interpretive approach towards executing these computational graphs, meaning dynamism is actually a lot easier to implement in that sort of framework rather than in TVM, which has a compiled approach, where we need to know things like the axes we're running reductions upon in order to generate the fastest code possible. So at this time, TVM overall does not support dynamism super well. And even when it doesn't necessarily generate the most fast code for it. Luckily, even though I've said all of these problems, a lot of the current models we see, which use quote unquote dynamic offsets from the ONNX framework, aren't actually dynamic, because things like the axes parameter or axes input I described previously aren't actually, true, black box tensors that you can only examine at runtime in order to get the values of. They're actually constants which we can fold away running some additional analyses. So right now, this is not a super major problem, but it does show cracks, potential cracks in the future. So if we go to the next slide, we're going to talk about some of the things that we're trying to do in order to fix this. So at TVM and OctoML, we sort of recognize maybe some of the deficits with dynamism in TVM. So we, of course, are trying to come up with projects in order to fix this and make other various improvements to the compiler infrastructure to better support these new, more modern workloads. So we call this project Relax, and it has a lot of exciting things that we're going to plan to extend into TVM. For example, we're going to support symbolic shapes and being able to propagate these symbolic shapes with computation, deduction, and establishment of invariants throughout these computational graphs. So if we look at this example before, we have a tensor of size n and m, which can be sort of inferred at compile time now, whereas in the past, we couldn't do this. Furthermore, we're going to add support for mutation, side effects, and better control flow, which should help us implement more complicated graphs like those required in training. Finally, we are looking at better establishing communication between lower level IRs and higher level IRs. And this might be useful, for example, in operator fusion, where at a lower level IR, you might very easily see that maybe we want to fuse these two loops together, and that might inform graph level optimizations further. So as sort of a sneak peek, it turns out that if you implement like a subset of the provided changes I mentioned before in sort of a somewhat hacky fashion with the TVM, you can actually use TVM as a compiler for training graphs. And this is really, really exciting because of course, the central part about TVM is the auto-tuning portion where we can find the fastest kernel for certain tasks. So what we see in this graph here is that when we use TVM in order to execute a training graph, taking a sort of a best of both worlds approach, where we take either the fastest TVM kernel or the fastest native executor for whatever GPU we're using, we see that we can actually see major improvements in performance. So on the left, we see BERT with one set of parameters, and we get a 40% improvement. And on the right, we see like a 27% improvement. We believe this will set the framework for using TVM as sort of a backend executor for many training frameworks in the future.
Thanks, Andrew. And hopefully you enjoyed that. I know we compressed a lot into a little time. And if you're interested in learning more, definitely check out tvmconf.ai, where our 4th annual conference is coming up just around the corner in December. and we'll be opening registration soon. Check out our website and sign up to learn more, or reach out to me directly if you have any further questions. Would love to chat. Thanks so much for your time.